This video is about detecting new nominal values in a test data set that are not present in a training set. This is important because a model built with training data that has to deal with test data containing new values for attributes may behave in unpredictable ways. Rapidminer does detect this, but it can be easy to miss, so this video shows a way to check using Rapidminer operators that you can incorporate into a systematic process for data quality assertion. So we'll look at the following things. First of all, we'll look at some training and test data that has this issue, and we'll use it to build and apply a model. We'll also look at the error message that's output to the Rapidminer log. Then what we'll then do is use various operators, starting with nominal to binominal, which lets you itemize attribute names and values. Then we're going to do a little trick and use various conversions to weights and back to an example set as an alternative to using the transpose operator. And then finally we'll do some manipulation by appending, aggregating and filtering, and the end result will be that we'll find attributes with new nominal values. So let's start with the data. So again, as usual, I make just some fake data, and I'm using an operator called generate nominal data here, and it basically lets you create a number of examples, and you can dictate the number of attributes and the number of values that those attributes can take on as nominal values. So in this case, this training set has 100 examples, 5 attributes. There'll also be a label, and each attribute will have 5 possible values. So far so good. This test data is the same operator, but this time I'm stipulating 6 values for the nominals. We might as well run that. So I'll set a breakpoint here so we can look at the data. So this is the training example, and you can see 100 examples, 5 irregular attributes, a special one. And if I look at the statistics view here, you can see, sure enough, for attribute 1, for example, there are 5 different values ranging from value 0 to value 4. The label itself has 2 values, and essentially what we're going to do is predict this label negative or positive based on these attributes here. And this is the training set. So if we now look at the test set, it looks very similar. But if we look at the statistics now, you can see that as set up, there are 6 possible nominal values. Okay, so that's the shape of the data. Let's build a decision tree on it. Now we're building a decision tree using the training data, and as you know, what the decision tree lets you do is, if you have a new example that you don't know the label for, don't forget the label is either positive or negative, you feed the example at the top of this tree and you can sort of read off what to do. So the tree's been built so that attribute 2 is clearly the most powerful prediction attribute. So basically, if attribute 2 has the value 0 here, equals value 0, then that means the label is positive. If attribute 2 has value 4, then it's mostly negative. If it's value 3, it's mostly negative. And if it's obviously value 1 or value 2, then you look at the other attributes. Now clearly, the training data has 5 values for each of these attributes. So if you now present it with test data, which has 6 possible values, then clearly it won't know what to do. It'll get confused and won't know how to traverse this tree. Let's have a look at that happening. We might as well just apply the model and run all the n to the performance vector. So a performance vector, so it's sort of done, looks like it's worked. Okay, if we look at the example output from that, and it's made a prediction. You can see it there, and it's most of the time confident about how good the prediction is, but you can already see a hint that it doesn't know what to do in certain cases when there's a missing value for the confidence. And the reason for that is because this particular example has one of the attributes where the value is one that the training data hasn't seen. So you can sort of get a hint that something's going wrong. It doesn't flag up an error in the execution, but it's still had a go. I guess it's what it's done. It's used the other attributes to sort of get as far as it can down the tree in this case, and it's still come up with a prediction, but you don't know how confident it was, because I suppose it's not that confident. And if you can also look at the log, which is here, and it's correctly said that there are in fact 6 possible nominal values that it's seen, but it only saw 5 in the training. So the point is, it's done a job, and other operators, other modelling operators, classification operators will no doubt continue to do a job. Some may fail, I don't know off the top of my head. But the point is, it's not exactly obvious that this has happened. So what the rest of this process does is show some operators you can use to find new nominal values and output them as an example set. So the way it's going to work is this make data makes training and test data here, and training and test data down these outputs here. So this path here is for training data, and this path here is for test data, and these two paths are the same. So we'll just look at this path here. So the first thing we're going to do is do nominal to binomial. Let's set a breakpoint on that, and let's do it before and after, so you get a clear view as to what's going on. So nominal to binomial, what it does is it basically looks at every possible value and creates a new attribute, which is either set to true or false if the original input data had that value for that attribute. So here's the input data. At 1 is value 0 for this example. At 2 has value 2. If I run this, you can now see that it's basically created 5 new attributes, and you can see from the names where that attribute has come from, and the value true means it if you remember, at 1 had value 0, so therefore this new attribute is set to true and all other at 1s are set to false. And if I recollect, at 2 had value 2, hence this is set to true. So you can see straight away that there are 25 attributes now that have been created, because there were 5 original attributes, each with 5 possible values, so there are 25 combinations, hence 25 new attributes have been created. All very good so far. Now what we're going to do is use a bit of a trick and do data to weights. So if I just continue this, you'll see what data to weights does. It basically creates a weights object. It's a bit like an example set, not quite, but basically for every attribute in the input set, the weight is set to 1 in this output weights object. Okay, now that's fine. But to use it, what we're going to do is change it back into an example set. So I use the weights to data operator. We'll carry on. Now what you're seeing is an example set, and it's exactly the same content as the weights vector. But now one of the attributes is called attribute, and essentially it's what was the attribute name in the previous nominal to binomial operation, and obviously there's a weight attribute here which is always going to be set to 1. So that's the training data. And what we're going to do, we're going to compare that with the data from the test path, and we'll do it just before this append operation. So we'll break before the append and then we'll break after it. So this top line was the training data, this bottom line was the test data. So if I set a breakpoint now just before this append operation, you'll see the 2 inputs to the append. So this was the training data, we just saw that one, and the test data now is very similar, but there are 30 examples in this because, as you can imagine, there are 6 possible values for each attribute. So there are 5 attributes, each with 6 values, hence 30 combinations. And now by appending them, we create 25 plus 30, 55 examples, and you must get a hint as to what we're going to do next. We're actually going to count up, do some aggregation, and count how many times these attributes appear in the pairs, and every time there's only one, it means it's new. Okay, and the way we're going to do that, we're going to do aggregate, and what we're going to do is group by the attribute name, the attribute, bit of tautology there, and we're going to aggregate by simply counting the weights. So if I set a breakpoint after the aggregate operation, you can see that it's reduced down to 30 examples again, which is the superset of 25 and 30, and now this count weight attribute basically is saying how often it's seen that value from the 2 inputs, from the test set and the training set. And sure enough, we get a hint that actually at 1 value 5 it's only seen one of those. So just to finally eliminate all of the spurious things we're not interested in, we're going to do a filter examples, and we're simply going to say if the count of weight is 1, keep the example. So let's just run that to the end. And sure enough, here we go. So this now is an attribute, this now is an example set showing which attribute and values are new in the test data. Very neat, very relatively simple. So this would let you, if you wanted, you could then do some more manipulation on this if you wanted, and you could even automatically detect this, flag up some problem to allow someone then to do something about it. So you always generally do need to handle this sort of scenario, and of course the thing you do depends on the particular circumstance. But anyway, by being able to detect this, it lets you build a bit more quality into what you do, so it's a bit more hands-off and will just work without having manual intervention. So I'll run it one more time. We'll just go through the various things. So one by one, this is the example set, the test set with the training model where confidence has been predicted, where labels have been predicted rather, with confidences that are missing when one of the values is unknown. The performance vector for that, it's still managed to come up with something. The decision tree, and you can see that obviously value 0, 1, 2, 3 and 4 are included. And then finally these are the attributes and values that are new in the test data.